Yeah, so what I'm going to talk about today is joint work with Vishu-Kern. Right. So maybe first start with some observation that's sort of interesting, I think. So so let be, well, throughout my talk, F will be some infinite field, say. Infinite field. And let's look at this matrix. Negative T1, negative T2, negative T3, where T1, T2, and T3 are variables, so I can also write it like a linear combination of three matrices. That's another way of looking at it. You know, where well, x1 is 0. Sorry. Etc. So this is always a skew-symmetric matrix, and we know a skew-symmetric matrix always has like even rank. So this matrix, right, is never invertible, right? So it's singular for all choices of T. Okay. So, but let's do something different. So we can wonder what happens if we, instead of think of this T1, T2, T3 as variables, let's think of them as blocks of 2 by 2 matrices and see if that makes any difference. So, so let's think of these in, say, 2 by 2 matrices. So if you want to see if this matrix is invertible, we can do some, by the way, this should be, just to make sure, this is a negative. So if you start with this matrix.
No, it's a 6 by 6 matrix.
Yes, so the T's are, think of this T, I write the same thing, but it's now, right, it's a 6 by 6 matrix. Or 3 by 3 matrix in non-commutative variables. That's another way of looking at it. So let's assume that the matrix T1 is invertible. Then we can do some elementary row operations. So let's multiply this with negative T1 inverse, and this row with T1 inverse. And let's also switch these two rows. All right, so just do several. And so this is, we multiply this with this block matrix, 2 by 2 block matrix, but that's still elementary row operations. And so now we get here 1 T1 inverse T2, 1 0 minus T1 inverse T3. This didn't change. And so we can do some more operations, subtract T2, the first row, from this row, and T3 times second row. And so we end up with this matrix. Zero, 0. And then here we get T2, T1 inverse T3, minus T3, T1 inverse T2. Okay, and now you see that this is, if these are commuting variables, this is equal to 0, but if they're non-commuting variables, then this doesn't have to be equal to 0. In fact, if you just take, say, T1 to be the identity matrix, then that's just a commutator. So if you take T2 to be this matrix, and T3 to be this matrix, then, this entry here, this is equal to, if I didn't make any mistakes, to this matrix. So it's invertible. Right. So if you make these substitutions, and this will become a 2 by 2 identity matrix, etc. So now we have a 6 by 6 invertible matrix. So, by the way, maybe I'll call this matrix xt. But there are different ways of thinking of xt. So if T1, T2, T3 are these 2 by 2 matrices, then this matrix is invertible in this context. Okay, so that's kind of an interesting phenomenon.
Do you assume that the field is infinite?
Well, it's later. We'll use that. But basically, just want to have, you know, if you have a polynomial, I just want to be able to say, well, if I have a non-zero polynomial, I can plug in some numbers and get something non-zero. And if you work with a finite field, that might not be true.
Almost everything will work for large enough.
Yeah, that's right. But, right. So a slightly different way to look at this is we can also look at X to be, say, the span of these 3 matrices. And then we could sort of take the tensor product, or maybe we should say Kronecker product. So we can view this tensor product as lying inside 6 by 6 matrices. So that's sort of this construction of substituting 2 by 2 matrices.
In all possible ways. When you write
In all possible ways, yeah. So exactly. So for every variable ti, we can choose a matrix. And so this has no invertible matrix. And this has an invertible matrix. It's basically given by that. And if this has an invertible matrix, then it's also true that sort of generically a generic element in here is invertible, or general, like. So the matrices that are not invertible, they are sort of a Zariski closed proper subset of this vector space.
another way is just choosing random 2 by 2 matrices, even with small entries, will be
Right.
given on
Yeah.
singular.
That's another way of saying that. Okay. So we use this notation. So this is sort of the blow up of X. I guess a blow up of order 2 in this case. So more generally, if you have some subspace, say, of 2 by k by n matrices, then we define xpq to be we take p by q matrices, take the tensor product with X, and that lies now inside the pk times qn matrices. And we often use the convention, you know, this here is then just what you do with p by p matrices. That's just a shorthand notation. One more notation is we define, say, rank or Rk of X to be the maximum of the rank of an element in A, sorry, a matrix A that lies in X, right? And if it's the maximum, then again, if you take a random element, it will be this maximum. Okay. Maybe I'll use the other blackboards. Okay, so one very useful result is the so-called regularity lemma. So this by Ivanios, Zhao, Subramanian. And this says the following. So a very curious property. I found it very surprising when I first saw this, but I don't know. So if you have a subspace of K by n matrices, and now we take these blow up, then and we take the rank of that, so the maximum rank appearing in this subspace, then this is divisible by D. Okay, so some kind of integrality condition. So I'll give a sketch of a proof which is different than the proof they gave, but it sort of ties nice into sort of classical ring theory, I guess. So I mean non-commutative rings. So so let's say we have this well, maybe we have this some linear combination. Right, which is associated to, you know, if you choose a basis of X here. Now I'm gonna think of this Ti as a D by D matrix, but a generic D by D matrix. So I'm gonna say here, I'm gonna use variables. I'm gonna use upper indices because I'm sort of running out of space. Ti 1n, sorry, 1d, all the way up to Ti d1 up to Ti dd. Where this Ti, j, k, these are just elements in, sorry, these are just variables. So these are commutative variables. And so this matrix here, this matrix lies in the D by D matrices, right, with entries in this commutative ring, with where you add all the variables. So now with this following situation, so we have this ring. Maybe I should have given it the name, but I'm not going to use the ring anymore.
But the proof, you know, will not give an intuition why this.
I think, yeah, I don't know.
Because it refers to something that's something somewhat mysterious.
Yeah, it's still mysterious. Yeah, I agree. Yeah. So inside here, we can look at the ring generated by these T1 up to well, that's Tm. So that's and so maybe I'll call this say Rd. Now inside Rd we have a center. And the center is actually an integral domain. So it has a quotient field. And now we can construct the following ring. We take sort of the tensor product of the quotient field over Zd with the ring Rd, and maybe let's call that SD. And this is a division ring or a skew field. And so this is.
I don't know. I mean, anybody who doesn't know any of the terminology should ask him.
Yeah. Yes.
Yeah. Can you remind me what a quotient field and division ring are?
Okay. So if you have, so for example, if you have the polynomial ring, right, then you can also look at all the quotients. So that would be the quotient field. So you can do this for any commutative ring, as long as you don't have any zero divisors, etc. Now, so a division ring is like a field, right? But this is sort of a non-commutative version. So every element, so it's a ring that may not be commutative, but every element that's non-zero has an inverse. So that's a division ring or a skew field.
So in the usual polynomial ring, the center is trivial, it's just a field.
Right. Yeah. So this is a non-commutative ring because it's it's a bunch of matrices, and so these are the matrices that commute with all the other elements. And so essentially, this SD is the ring that you get by allowing things in the denominator that lie in the center. That's basically what this is.
These are diagonal matrices. I mean, scalar matrices.
Yeah. So these are scalar matrices, but the diagonal entries may be some complicated polynomials. All right. So now, so if we start with this matrix XT, okay, so this is a, so then we can do some elementary row operations. So what kind of elementary row operations? So this is sort of a non-commutative setting, but it's just like what I did over there. So this kind of elementary row operations, and maybe also column operations. So I can just multiply rows on the left with some element in this ring here. And just like in the commutative case, you can use elementary row and column operations until you get a matrix that's of the shape where you have sort of ones on the diagonal and then zeros, right? And the rest of the entries are zeros. Where you may have like R1s.
The rest of the entries on the other.
Everything else is zero.
Yeah, but in the by our block it's only.
Yeah, there's also zero.
Okay.
Okay. Yeah, maybe I'll write like this here. So like a block matrix. All right. By the way, I forgot to say this. Right, so this is a theorem by Amit.
This is a mysterious one.
Yeah.
Wait, so the top right is not going to be all zeros, right? I mean, this is reduced row echelon form.
Yeah. So sorry. Row column operations also. Yeah.
Well, what's your division ring? You can do the thing that you're using
Yeah.
in the commutative setting.
Right.
That is the only question that I cannot answer, but I'm really interested in is why it is true.
Right.
You know, but
Right.
now we have it, so we can.
Yeah. Now, along the way, we had to invert some elements, right? So just like there, I assumed that T1 is invertible. So if I do these elementary row operations, then I may have to assume that certain things are invertible. Well, of course, there are invertible in that ring, but but I'm going to invert some elements. So let's say that these polynomials in SD are inverted. But now, now we're sort of done in a way. So maybe I'll just say, we just take random choices, or generic enough, but anyway, choices for all t, I, j, k. For all these commutative variables, we can just plug in random numbers. And then these matrices are all invertible. They may be complicated expressions like, something like that over there, but they're all going to be well defined and invertible. And so now we just basically have this matrix, and we do elementary row operations of this matrix, and we end up with a matrix. Now these are just d by d identity matrices. So xt is sort of row column equivalent to maybe write like this, IRD. In other words, the rank, or I call it RK of X, is equal to D times R. In particular, it's divisible by D.
So you use this theorem in order to do the row and column operation?
Yes.
Well, everything that's not zero can be inverted.
Yeah.
This is what the theorem says.
Right.
Otherwise, it's not clear that you can reduce.
Right. Yeah. So it's a little bit mysterious. Okay. I should say that some, advantage to their approach, because in many ways, it's constructive, but it's probably take long to explain. All right. So now we make the sort of definition. So we defined the rank of X, but now we also define the non-commutative rank of X, which is one way of defining it. Well, one way of okay. Well, here's one way of defining it, but there are different ways of defining it. And maybe it's not obvious that all these things are equivalent, but yeah. So we know that this is divisible by D, so we can take the quotient and we can look at the maximum over all D. But for large D, this will be constant and equal to this maximum, so I could also write it like this. Right. I mean, these are integers, so this limit just means that eventually it's just constant, and that's the limit. Right, so this is an integer. So that's the non-commutative rank of X.
Yeah, these ratios are increasing. So
they are eventually increasing, right? So they may not. I think they're not always increase. What? I have to think about it, but I thought they were not always increasing, but eventually, or not?
No, I think they are increasing, but it's not obvious if you put the generic elements, but if you allow all elements, all matrices, then they are increasing.
Okay, well, I have to think about it. It doesn't matter. I think there's some subtlety there. Anyway. Well, another way of thinking of this non-commutative rank is sort of, you know, just by in terms of these elementary row and column operations. So you start with this matrix with variables that are non-commutative variables, and you just keep doing row operations and column operations, and then at some point you get just ones on the diagonal, and this non-commutative rank is, you know, the number of ones you would have on this diagonal. So that's another way of thinking of non-commutative rank. So we have the following result. Okay. So maybe the non-commutative rank is smaller than. So maybe first say it's less or equal than 2 times the rank of x. So this is due to Flanders.
Here x is a matrix?
Matrix space.
Yeah. So yeah. So x is a
Space of matrices.
a space of matrices. Yeah. Now for that, the non-commutative rank makes sense, right? Yeah. So we only define really. Although I guess you could anyway.
Sorry, wait, you fix x1 to xn and then you ask for the maximum or the...
Well, it's not going to be. It's going to be independent of, you know, the choice of the basis, right? But so it really depends on this x, which is the span of x1 up to xm.
Okay.
Yeah.
Oh, this is what you said.
So, right.
Why do you define it with matrices rather than with general non-commutative?
It's as general as any non-commutative.
Okay, so why do you define it with matrices then?
Sorry.
Why do you define the non-commutative rank with matrices rather than with general non-commutative variables?
Well, there are various subtleties, but you could sort of construct sort of a general ring, but sort of the non-commutative version of a quotient ring is actually already complicated to actually define it even in a proper way. So there is some notion of that, sort of some kind of free field, right? And you could actually define it in terms of that. But I didn't really want to introduce that, so that's why I just defined it in this way.
The main difficulty is because it's hard to know when an element in this field is 0.
Right.
So you can define it by you know, Gaussian elimination. You could, but the expression you get in the definition of rank, you can always say I want to diagonalize the matrix and count the number of ones in the diagonal. But when you do this, you get elements in the various other entries, and the question is how to tell whether they are 0 or not.
Yeah. Okay. So we actually proved that this is actually sharp inequality. So actually, this is also something that's maybe I'll give a sketch. This is actually not hard. So this x, let's say we have some subspace, and let R be the rank of x. So that means that all the matrices in here have rank at most R. So we can just choose one that has rank R. And doing some elementary row and column operations, we can actually assume that, well, we actually can assume that this matrix here lies in X. And this actually implies, if you think about it, that all the matrices in X are of this form, right? Where this is, R rows and R columns here, or vice versa. I mean, right? Because if you have any matrix, right, where that has a non-zero entry here, and you sort of add, say, some random multiple of this to that matrix, then the rank is going to be more than R. So it sort of forces all the matrices to be of this form. right? But but now, if we have some matrix in X, say is of the form C, D, E, say, if this lies in this space X, then the non-commutative rank of this matrix, C, D, E, is less or equal than, and this inequality is straightforward, the non-commutative rank of this matrix plus the non-commutative rank of that matrix. And non-commutative rank of this matrix is at most R. And this matrix has only R, this E has only R columns. So that also has non-commutative rank at most R. So we get 2R.
That's a Flanders.
Yeah, so this is a Flanders. Because of time constraints, I mean, there's just a small trick and some kind of induction proof that adjusts this to actually get the proper equality. But
Just Benjamin said, so in the example that you started with, the rank was 0, right? The 3 by 3.
The 3 by 3. The rank was
Okay.
2 and the non-commutative
Yeah.
rank was 3.
yeah, it's a
Oh,
good,
the rank.
yeah,
I didn't think about the rank. I thought about
yeah.
I thought
Yeah, I should have gone back to that example. But that example shows that the rank and the non-commutative rank are not the same, right? So the rank is 2, the non-commutative rank is 3. Now there are other examples where the gap may be even more. And there are also examples where just substituting 2 by 2 matrices might not be enough. Maybe you need 3 by 3 or 4 by 4. So, okay. All right. Actually, also interesting is actually for a while people thought that maybe the rank, the non-commutative rank, is always at most 1.5 times the rank. But this is actually not true. So you can actually get the ratio arbitrarily close to 2. And so there's the following example. So if you have a vector space, say, of dimension 2p plus 1, then you can look at the exterior power, right? So this is a vector space of dimension 2p plus 1, choose p. And well, this has also the same dimension. And now we can actually make a linear map. Once we have an element in V, we can just do, say, some element in B, we can just map it to A wedge B. Okay, so using exterior powers. So
These are like the determinants of all sets of size P of a subset of
yeah. So if you have an n-dimensional space, then this wedge NV is sort of a well, so one way of defining it is sort of as a quotient of n-fold tensor product. And these are all, well, one could think of this, or let's say p-fold tensor product. And these are all the tensors that have this property that we have this action of SP on it. And if, so these are all the tensors such that if we have an element of SP and apply to it, then the way it acts is by the sign. Okay? Inside here. So that's one way of defining the pth exterior power. Okay, well, at least in characteristic not 2. Anyway, so another way of thinking about this is as a linear map from V to hom wedge PV wedge P plus 1 V. And this here we can think of just as maybe, well, let's just capital N, where N is this number here. And so now we have a subspace in here, and this example it gives you the following. So maybe we call this X to be the subspace. So in this example we get the rank of X is equal to, turns out, this binomial coefficient, but the non-commutative rank of X is full. So that means it's actually this number 2p plus 1 choose p. And if you take the quotient, then this is 2p plus 1 over p plus 1, which of course tends to 2 as p goes to infinity.
So this Landsberg-Ottaviani example.
Yeah, so it's basically, yeah, this appears in Landsberg-Ottaviani.
There is a way to view this matrix of variables just as an inclusion matrix of p subsets of 2p plus 1 by, you know, p plus 1 subsets. The only, or disjointness matrix, if you want, but it's not, but it's variables. There is a canonical way to explain it without the West product or anybody who wants, but this gives you the signs, and the signs are critical for
All right. I guess I could have made it a little bit more explicit, but
How do you get the signs from the inclusion?
it has to do with the ordering of, I mean, more or less, every subset, you know, there are 2p plus 1 elements. Maybe don't worry, you are not losing time.
Okay.
There are 2p plus 1 elements, so rows are rows corresponding to p subsets, and let's say columns correspond to p subsets of the same set. And in the case that they are, you know, if they intersect, then it will 0. If they are disjoint, then there is one variable missing. You see here, one variable missing. And so you put a variable there, and the only question is what sign. And the sign depends on its location, whether its location is even or odd in the order.
yeah, so you could think of as a basis, you could take, say, all where I1 we have this IP, and now I define, say, a function f, maybe let's say xj, does the following. This sends this to I1, I2, IP, where I add a j, right? So these kinds of things are basis of the first vector space. But here we have the convention that if I have IPJ, or in general, if you switch two entries, you switch sign. And if two entries here are the same, then this thing is just 0. Okay? And so that defines a map from xj where, you know, these things that are exactly 2p plus 1 over p, choose p of these guys, they're actually exactly 2p plus 1, choose p plus 1, because we can always sort them from small to large, and then we get maybe some plus or minus sign. Okay, and that's how these xj's are defined, and then we just take some tj xj, and that's some linear matrix that with p variables now. And if you do the simplest example, where you take say wedge 1 v, where v, the dimension of v is equal to 3, to wedge 2v. Sorry?
It's 2p plus 1 variables now. The number of variables. Matrices.
Yeah, you're right. Thank you. Yeah. So this is the case P is 1. Right? So where we have a three-dimensional space, wedge 1v is just v, and this wedge 2v, which is also three-dimensional. And then we get this thing in 3 variables now, which is exactly this matrix that I started with in the beginning. So that's actually a special case of this. There's actually a nice application to this. I cannot say too much about this, but you know, if you look inside this tensor product, or if you want, you can think of this as three-way arrays. Okay, so these are, if you have a tensor in here, right, then we can write a tensor sort of as a sum of pure tensors and the smallest r for which this is possible is the rank of the tensor T. So this generalizes the notion of a rank of a matrix. Now it turns out it's very hard to find lower, so for matrices the rank is very easy to compute, etc. But for tensors, elements in here, the rank is usually very hard to compute. In fact, one can show it's an NP complete. But in some cases, these examples actually allow you to give lower bounds for certain given tensors. So it's sort of a nice application. So these examples have actually nice applications.
So what kind of tensors do they have to be so that you can get lower bounds?
In fact, a generic tensor actually this would work.
Yeah.
But the only thing is the lower bounds that you can get will never be more. You know, the lower bounds will not be better than 2n. So the best lower bound you could get is maybe 2n minus 1 or something like that, because we know the non-commutative rank is less than 2 times the rank. So there's a limitation. It's a pretty strong limitation. But all the other methods that we know for finding lower bounds actually worse. So you know, there's a Kruskal's condition. You know, the best you can get with that is 1.5 times n. And this also gives lower bounds for the so-called border rank, but I guess I don't want to really go into that. But that's even harder.
What tensor is any symbolic matrix like this is a tensor, right? I mean, you can put
right.
The matrix as the base. You have a bunch of matrices that span your space.
Yeah.
Just put them one by one. That gives a tensor.
Yeah.
And
I
the
know
lower
tensors, but I'm asking what conditions on the tensors do you need so that this is useful?
That's well, this lower bound technique comes from this connection between non-commutative and commutative. Like it's very simple to see that for this tensor, when you line up the matrices on the basis of such a space where there is a gap between the commutative and non-commutative rank, you get this gap multiplied by n in the lower bound.
Yeah.
So this technique, like said, will never give you anything better than 2n.
Yeah.
We have no idea how to get explicit matrices. Tensors where the gap, let's say n by n by n tensors.
So we know if
that's the best you know.
That's the best we know.
Yeah. Yeah. So we.
It's much larger, right? I mean,
It's close to n squared. It's a constant n squared.
Yeah. So if you take a sort of a random tensor, the tensor rank will be over n squared. But the only thing, you know, the only methods that we have, we can show, you know, maybe 2n minus 1 or something like that.
It's a great challenge.
Yeah.
But Ran has a result showing that proving tensor lower bounds also gives surface lower bounds. So it's hard.
Yeah.
From Formulas,
for our logical
logical.
cells.
Yeah. Okay. Okay, so now no, I think I'm going a little ahead. So one fundamental question is, like, for example, in the example that I started with, you know, we could substitute 2 by 2 matrices and then the matrix became invertible. But in general, if you have an example like that, you know, how large should you choose the matrices such that you get sort of the rank that's, if you divide it by D again, that you get exactly the non-commutative rank, right? So in this definition, that's no longer there, unfortunately. Okay. So anyway, so this is what we proved. If you have, say, a subspace of n by n matrices, and let's say D is at least n minus 1, then the non-commutative rank of X is equal to the rank xd over D. So we know for a large enough D this was true sort of by definition, but this gives you an explicit bound of when we have equality. Okay, and to see this, we can sort of play a game. So if we define RPQ to be the rank of this blow up P and Q, right? You can wonder, like, you know, what are these numbers and what kind of properties do these numbers have, right? And so there are some obvious results. Sorry, that's greater equivalent. And also we have some convexity property. Yeah, and
These are P by Q matrices that you're plugging in?
No,
yeah, yes.
plug in, yeah.
Yeah.
Plug in.
Yeah, we plug in.
One is n by n, or it doesn't matter.
Yeah, yeah. So we start with some, well, it doesn't matter there I wrote n by n, but could be k times n. And finally, because of this regularity, we have RPQ is divisible by the greatest common divisor of P and Q, right? Because if P is Q, we know that, you know, RPP is divisible by P, and this you can easily deduce from that. And of course, similar properties for the first quadrant are also true, so I'm not going to write it down. So I'm just going to do an example like how you can use these properties to prove actually something. So I'm just going to do an example. Let's say we had a subspace of 4 by 4 matrices, and let's say that the non-commutative rank was 4. So that means that this is equal to the rank of xd divided by d for d large. Okay. And let's say for the example, let's say So the idea is to get this d very small, right? So the idea is to prove if you have this, if this is true for d, to prove for d minus 1, if d is large enough. Now, for the sake of the argument, let's say that this is equal to, say, x5 divided by 5, right? Then we could look at the table for RPQ. Let's say this is P, this is Q. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
In every block you're plugging the invariant matrix.
Yeah, yeah. So and not exactly this value, but say a lower bound. So in every entry, I'm going to put a lower bound. So here we have a lower bound. We know that this is equal to 20, right? Because for this divided by 5 is equal to 4. And this is x55. But now if we use this convexity.
Can you explain the matrix? The matrix is not a matrix of matrices, it's a matrix of numbers.
No, but
Of these numbers.
Yeah,
the numbers
right.
are PQ over there.
Yeah,
So it's
yeah.
okay.
Yeah, so I'm just writing a table for this RPQ. So if you look at this here, this column, from this property, this convexity property, shows that this has to be at least 1/5 of 20. So this should be at least 4, and etc. So you get all these lower bounds here. And same here. So 16, 12, 8, 4. Right? Now if you look at this row here, then this entry should be at least 4/5 of 4, right? So it should be this entry should be at least 4/5 times 4. But then, you know, there's 16/5, that's more than 3, so it should be at least 4. So we get, this has to be at least 4. And similar, this has to be at least 3 to 1. Now, if you look at this entry here, this has to be at least 3/4 times 16 plus 1/4 times 4, which is 13. By the convexity. Yeah. So this is a convex, you know, if you have this condition, then it's just a convex function. So you also get this property. So this is at least 13, but now we know it's divisible by 4. Right? So now we use the regularity. It's divisible by 4, so it has to be at least 16. So we get 16, 12, 8, 12. You know, you can actually give all these lower bounds. Okay, so that means that this thing is now also true for D is 4. Now we can push it a little bit more, because if this rank, if the rank of this matrix was 1, then it's easy to analyze, and you can show that this couldn't be 20 over here. So we actually know that this is at least 2, and then that sort of implies that this has to be at least 4, and this has to be at least 3. And then we can look at this entry, should be at least 2/3 times 12 plus 1/3 times 4. So it's 24, 28/3. So if we round it up, that will be 10. So it's at least 10, but it has to be divisible by 3. So it has to be 12, etc. So anyway, so we see now that R33 is 12. So in other words, if you take the rank of x3 divided by 3, this is 4. Okay, so we already had equality for D is 3, right? So that's basically the argument, but done in this particular example.
What does non-commutative rank 1 look like?
I think it's the same as commutative rank. Yeah, if something is commutative rank 1 is, you know, if 1 is 1, then the other one has to be 1. But if one is 2, then the other one could be 3, right? So in our example.
So okay, so you showed some example, but this theorem really only uses these few properties, right? So in order to prove the general theorem, it is only enough to know all these inequalities?
Yeah, I mean, I just basically gave the proof, but you know, if I write it down in general, it's sort of, you know, this is the idea of the proof, basically. If you work really hard, you can actually sometimes prove better bounds, because you know, you could use some other numbers. You know, if you exploit this even more, you could sometimes maybe prove n-2, or yeah, n-2 instead of n-1. But so far, I don't think you get something that's really substantially better than, you know, nothing better than O of n. You know, it might be n minus some small function that goes to 0 when divided by n.
There's after they did it, there's another proof by the same IQS, Ivanov, Tiao, and Subramanian, which does not use the context. It's more direct.
Right.
More purely in algebra. But it's slightly weaker, maybe n plus 1 or something like that.
Yeah. N plus 1, I think. Okay. So how much time do you have left? I'm sort of out of time, but
10 minutes.
10 minutes. Okay. So maybe I'll just try to briefly look at some applications. So one application is sort of this tensor to algebraic complexity theory. That's an important problem for some complexity problems. But here's another where you look at non-commutative circuits. So maybe I'll just draw a circuit like this. Start with some things, and then maybe I take here the product. Maybe here I take the inverse. Maybe go right inverse, and maybe I take the sum here and take the product here. So this is a circuit for the which gives you 2 times T1 plus T2 inverse multiplied by T1, right? So that's a non-commutative circuit. And now now if you start with a non-commutative circuit, you can sort of make a linear matrix so this is a construction by, I'm not sure if I put that groups or how you put that, Robisch?
Check, yes.
Yeah, right. And Avi. And if this has size, say d, where the size is just the number of gates, then this has a size at most 2d. Now, if you have a non-commutative circuit, then one fundamental question is, you know, whether this thing is actually defined. So, in particular, if you take the inverse of something, then you know, you can't take the inverse of something that's 0, right? So. So the question is whether this circuit is defined. So maybe I'll say this non-commutative circuit defined either in this sort of ring that I defined before, or maybe I'll just say, you know, for some matrix input. but if and only if you do this construction in a certain way, you get this property that this is true if and only if there exists this matrix XT is invertible.
Yeah, I have two comments. One is that it's for that this construction is for formulas, not for circuits. It's only for this size, the connection between the size of the matrix and the size of the circuit.
Yeah. Okay.
Just for formulas, not for circuits.
Okay.
This is, the second is that this construction is basically due to Kohn. We use it and we
Okay.
change a bit, but it's basically due to Kohn.
Oh, okay. So, hi. All right. So now, so with invert, maybe I should say your full non-commutative rank, right? So now, well, so now with our result, we get that this is true if and only if there exists some t in, say, so if and only if you can find 2D by 2D minus 1 matrices such that xt is invertible. So in principle, that would give you sort of a randomized algorithm for determining whether some formula is defined, well defined. But there are also some. Now this also gives you a way of testing rational identities, because you know, if you have some formula and you want to know if it's zero, if you take the inverse, then it's only defined when it's non-zero. So this gives you a way of testing whether something is zero. But now, but actually, there are actually now recent progress. There's some good now polynomial time algorithms, deterministic actually, for rational identity testing. So for over the rational numbers, there's a paper by Gurvitz, Olivier, and Wilkinson. And there's also a different method.
But this follows from this book?
No, actually
No,
not.
I mean,
But what he's going to say will follow.
No, but why?
Now, so for large,
Also,
yeah,
no,
it's
I know that chronologically it was before, but I'm not going to follow.
so for large field.
no, sorry. So yeah, this work needs an upper bound on this blow-up.
Right.
So what they just proved is the linear blow-up is enough to get the
Yeah.
non-commutative rank.
Yeah.
So
But
it's certainly it can be used in the proof, but the proof in that paper
yeah.
relied on an earlier result of how we just gave an exponential upper bound
Right.
to the blow-up, which was sufficient.
Right, exactly. So for this result, you don't really need it. So for large fields, with a different method, was by the three people I mentioned earlier, Ivanios, Xao, and Subramanjan. And they use sort of also results that are sort of similar to this result, where you have this kind of bounds.
Yeah, they need a polynomial bound on the.
Yeah. But they also really try to make things sort of really constructive and actually, anyway. Now the last thing, and maybe I'm just going to write a consequence without but this is sort of what was announced in the title of my talk, so I guess I have to say something about it. So one main application is invariant theory. So if you have, first of all, if you have some reductive algebraic group, anyway, all the examples I'm going to do are reductive, so don't worry about it. And V is some representation of G. And let's say, for the sake, let's say that this is algebraically closed. Well, maybe I won't need, for the statement I'm going to write, I probably won't need this. So, so then this group also acts on, you know, the ring of polynomial functions. So ring of polynomial functions on V. And then you can look at the ring of invariants. Okay, so this is sort of a classical. So these are all polynomials that are invariant under the group. And this is a subring of this ring. And fundamental question is, you know, to find generators of this ring, and preferably to find generators in low degree. Now, as a consequence from this result, maybe I shouldn't write it out, we get a nice result in one particular example. So if we take V to be the n by n matrices, we take m copies, so elements in this vector space are just m tuples of n by n matrices. And if we take the group G to be SLN times SLN, so these are basically row operations and column operations, but only with invertible matrices. Like then if you look at the invariant ring, so maybe write like this. So SLN cross SLN. So for example, if you have just one matrix, right, then one invariant polynomial is the determinant of the matrix, right? If you multiply the matrix with something invertible on the left or on the right that has determinant 1, then the determinant doesn't change of that matrix. But more generally, this is generated by invariance of the following form. If you have x1, x2 up to xm, we can take this sort of Kronecker product with some matrices and then take the determinant where T is matrices of size, and here with D less equal than say m. If I write it like this, I think m times n to the power 3. But if you look at the degree of this invariant, it's actually times n. So the upper bound for the degree of the invariants that generate the invariant ring will be m times n to the power 4.
And the previous bound was exponential. So
yeah, maybe that's good to point out. Yeah, so the previous bound was exponential, which was already an improvement on the bound before that used factorials, and yeah. Okay, I'll maybe stop here.